Hi everyone, I'm Yannick, CEO and co-founder at Arcium, and today I want to introduce you to the encrypted supercomputer, which is what we're building with Arcium. So the big problem that we're solving with Arcium is that everything is public by default, everything on the blockchain is public, but there are some things that should remain private. And there's applications that become more powerful when they can handle private data. And so the status quo really on a blockchain is that everything is public by default. If you want to have some level of privacy when doing DeFi, you require centralized exchanges to give you some level of privacy. And there's no true privacy-based applications possible, too many single points of failures, and a lot of MEV extraction. And when we think about powerful applications that could be enabled through privacy, we can think of confidential trading, confidential markets. Almost 60% of daily US spot volume, for example, nowadays is going through dark pools in TradFi. And so if we want to onboard these kinds of institutionals that require privacy when trading, when moving large asset balances, we require the corresponding infrastructure in a decentralized setting, right? And so confidential markets, private trading and lending, and MEV protection are a few use cases in DeFi that get enabled through private computing. At the same time, in the space of AI and AI agents, we have a lot of sensitive data that can be utilized for training models, but currently can't be utilized in an open, decentralized setting. So confidentiality and privacy enable confidential training, federated learning, trustless and secure autonomous AI agents, and even as far as end-to-end encrypted AI systems. Basically, what Arcium is a network that allows for any computation to be executed in a fully encrypted way with zero trust, fully decentralized, and as fast as possible. And Arcium operates over so-called encrypted shared state, which is state that nobody can see, yet this network is able to operate over without ever having to decrypt data. And we are offering composable execution for arbitrary smart contracts and off-chain workflows within our network. And in the past, we've seen a set of different privacy-preserving technologies, so-called PETs, privacy-enhancing technologies. The one you might be most familiar with are so-called zero-knowledge proofs, which have been utilized in what we call Privacy 1.0. There's also trusted privacy-enhancing technologies like trusted execution environments, which are based on hardware security modules. And then there's purely cryptographic encrypted shared states technologies like fully homomorphic encryption and secure multi-party computation. Privacy 1.0 really is this first frontier of privacy we've seen in the Web3 space, which is circling around financial transactional privacy. So examples would be Tornado Cash or blockchains like Zcash and Monero, where users, individual transactions are protected by encrypting them and using zero-knowledge proofs for settling these transactions without having to reveal all of the information that is part of those transactions. The problem really with these technologies is that no encrypted shared state is possible. So it's always individual users generating zero-knowledge proofs and having access to private data. But what we want is we want to build a blockchain. We want to build smart contracts where we can function the same way as if they were public, but now in a privacy-preserving way. And so that's what Privacy 2.0 entails, being able to operate over encrypted shared state where everything is encrypted and anything can be computed without decrypting the information. And that enables way more powerful applications because now we can't just have private depositing and withdrawing into Tornado Cash. Now it becomes possible to build entire applications that can also be compliant with full privacy guarantees. And so the technological choice that we've performed at Arcium really has evolved through the entire stack. So we've basically used all of these technologies and then landed at secure multi-party computation, because all of the other technologies fail to deliver both user experience and security that we require for this Privacy 2.0. So at Arcium, we use secure multi-party computation, MPC. You might be familiar with the term MPC from MPC wallets, but MPC at the end of the day, as a cryptographic primitive, allows a set of parties to jointly compute a function over distributed private data, where all inputs remain private and the outputs can be encrypted outputs, again fully private, or can be public outputs that can be settled transparently on a blockchain. So MPC is this set of protocols, this cryptographic family of protocols that allows this kind of computation. Again, we can't really use it seems like the diagrams I have, because the slides are rendered incorrectly. But basically what we have is we have encrypted data, and that encrypted data should flow into the blockchains. And on top of the blockchains, we have smart contracts with encrypted data in them. And then we have the Arcium network, which is able to process these kinds of computations in a confidential encrypted way, and is able to settle back to the smart contract encrypted, public, and a special type of encrypted results, where, for example, it's possible to encrypt data for some specific third party to see. And the core technology we are using for this is secure multi-party computation. And as I said, secure multi-party computation allows a set of participants to compute some function jointly over distributed private data without having to share that data. And so when we, in this example, have 3 parties, Alice, Bob, and Charlie, each single one of them has a secret, A, B, and C, and they want to compute the average of these secret numbers without having to reveal them. And so they can use secure multi-party computation for that. And it's a relatively straightforward process of doing that. And MPC splits into multiple phases. The first phase is the so-called secret sharing phase, in which every single one of the participants generates random data. And this random data is then correlated in a way where all random data generated by each single individual summed together would form their secret. And so they basically split their secret into 3 random values. And after doing that, they exchange those random values. So every single party in this computation where they want to privately compute their average keeps 1 random value to themselves and distributes 1 random value to each other participant. So everybody ends up with a set of random values, not communicating anything about the other player's secrets. In the next step, every participant now locally computes some functionality. In our case, this functionality is computing the average. So every single one computes the sum of these random values they have received. And computing the sum, again, generates a random value. So after performing this local computation, all 3 parties can reveal the final sums they've computed and collectively divide those by 3 and hence compute the average of their asset holdings. So that's a very simple kind of secure multi-party computation, and it always splits into multiple phases. Secret sharing, performing computations on multiple devices, and then at the end, collectively aggregating the final output. And what we've developed at Arcium is the so-called Cerberus MPC protocol. And Cerberus is a high-performance MPC protocol that comes with the lowest possible trust assumptions that a distributed computation can have. And that trust assumption is the so-called dishonest majority trust assumption, which always only requires a single honest participant within a secure multi-party computation in order to guarantee full privacy. And that's a big breakthrough because in the past, you're familiar with that from Byzantine fault tolerance in blockchain systems. Always more than half of participants in these kinds of distributed private computations would have had to be honest. But with Arcium, we always only require 1 honest participant. So anyone joining Arcium as a node in order to run confidential computations, can decide to become the single required honest participant. And we've further extended this protocol that we've developed over the last few years with so-called identifiable abort, which adds a new kind of cryptographic censorship resistance and oblivious data structures. And so in this diagram, we can now see that within Arcium, what's happening is secure multi-party computations, right? So if on the left side we have a blockchain with a smart contract and a so-called MPC execution environments, all that is happening is an execution is taking place within Arcium by taking encrypted data from the blockchain, transforming it into secret shares, where every single node within Arcium holds such a secret share, and then the Arcium network is able to run these multi-party computations. And at the end, a verifiable output can be settled back to the smart contract, where again, it can be encrypted state. So in the future, there can be another computation, but it can also be a public output. So there can be a asset transfer taking place, for example, or there can be an encrypted result dedicated to some specific party. So if someone is building a data marketplace, they can specify that the buyer of the data should, after the computation, have access to that data. So automatically within this multi-party computation, it will encrypt the data in a way where this corresponding party can access it. And so Arcium functions as a stateless computing network using existing blockchain networks as consensus and state layers. And the first blockchain network that we are supporting is Solana. So on Solana, we have parallelized on-chain mempools with local fee markers, which schedule those confidential computations that are taking place within Arcium. And on-chain really this on-chain functionality really serves as coordination for those encrypted computations taking place within Arcium, and that really is significant because in that concept, Arcium really is a network extension to Solana, because Arcium doesn't require anyone to bridge their assets or their smart contracts over there. Arcium remains a stateless, purely computational network that executes fully encrypted computations. And what that enables is for confidential on-chain applications that existing smart contracts can be extended with encrypted state and the confidential execution over this encrypted state in an asynchronous way via Arcium. At the same time, since Arcium is a stateless network, it becomes possible to run off-chain confidential computations with Arcium as well. And so what we've done with Arcium is we've built multiple things. We've built ArcOS, which is our distributed encrypted operating system, on top of which there's the virtual encrypted machines, MXEs, MPC execution environments, and we've designed Arcus, which is our custom Rust compiler and framework, which allows developers to simply add privacy and encrypted execution to their smart contracts without having to learn any new cryptographic paradigms. They can simply specify that some functions in their smart contract should be private and they're going to be executed within Arcium. Arcium operates in dishonest majority, which really is being highlighted by this diagram as incredibly powerful. There's always only the requirement that some arbitrary participant in a computation is honest. And performance-wise, what we've achieved is many orders of magnitude faster than fully homomorphic encryption, state of the art. And what we've also done last year is we acquired our largest Web2 competitor, who've been leading in confidential AI, in ThreatFi defense and healthcare. And what that enables us to do with Arcium is to offer confidential training and inference. And I personally see encrypted AI as the precondition for creating new economic incentives around data and on-chain models. And what this entails is the construction of end-to-end encrypted AI. And with end-to-end encrypted AI, and mainly currently machine learning and neural networks, this involves highly sensitive data that can be put into the training pipelines for models in an encrypted way without having to reveal it. So you never have to give up ownership over that data. And the models that are being produced are also fully encrypted and inference and predictions that are being run into those models, again, can take place over encrypted sensitive data. So it's end-to-end encrypted, and by access controlling these encrypted model weights through smart contracts, it becomes possible to create economic incentives and training feedback loops with more high quality, more sensitive, more encrypted data. And so I think I ran out of time. Here's a quick example of how the tooling looks like with Arcium. So here you have a normal functionality that some team developed for building dark pools, so fully encrypted on-chain order books with Arcium. And it looks like normal Rust code because it is entirely normal Rust code. And one of the big breakthroughs we've done is build this powerful compiler, because in the past, if you wanted to build something like this, not just on the infrastructure level of being able to process something like this, just from a developer experience level, you would have had to build this amount of cryptographic code. And with Arcium, all of that is being taken care of by our dedicated tooling. Thanks for your attention.